All right, welcome everybody. This is our last section for Chapter 3. This is going to be our study of mathematical modeling, which is basically some word problems. So I know you've basically just started groaning right there because I said word problems, but they're really not that challenging of word problems. All right, so big things down there at the bottom of the screen that you see are regression and variation type problems. So we're going to start off with regression lines. Regression lines were also called lines of best fit back in Algebra 1. And basically, we're going to be just looking at some data and looking at equations already given to us. So if you remember, we used to use scatter plots, and then we would create trend lines or lines of best fit that would best describe the data. So you would get lines like this. You would say, okay, here's some data points, and if I drew my scatter plot, I would look and I go, hey, that kind of looks like it could follow a straight line. We had said it would have positive correlation because it had a positive slope. And then we could create the equation using some points and the y-intercept, that sort of stuff. And from that stuff, we could actually predict outcomes way out here in the future that weren't part of our data points. Like if this represented time on the x-axis and the y-axis represented, let's go something weird like income. Right? So time changed, income changes, and it should not follow a scatter plot, but just kind of bear with me here. We could figure out, okay, let's say the data stopped at 10. We could figure out, using the trend line, what would happen at 50. We could estimate, and it's supposed to be a line of best fit, something that would fit the data. All right? So what we're going to be doing today is kind of the simplified version of this. I kind of call it the baby version. This little thing here I just mentioned here is there's different types of regression, but for the most part, we're dealing with linear. So you'll be given a set of data, but you'll also be given a regression line, an equation that is said to fit the data. And what you're going to have to do is you're going to have to test to see if that regression line is accurate enough for the data. So for example, let's say you have this whole data set and they say the equation y equals 3.1x minus 5.7 is the regression line. And it then is going to ask you, hey, is this line good enough? And you're going to have to test it for all of them, but I'm just going to give you an example of what you're going to look at. So one of my data points is 3, 2.5. So what I want to do is I want to say, okay, what do I get if I plug in x equals 3? And just plugging in x equals 3, I get 9.3 minus 5.7, and I get 3.6. Now, 3.6 is kind of far away from 2.5, but it could be one of those things we call outliers, where it doesn't really go to the line, but most all the other data does. So that's why you need to test all of the data points in your table or in your set of points, however it's given to you. All right, so those ones are pretty straightforward, I think. What we're really going to get at is the idea of a variation. And the first one is what's called a direct variation. And this is all equations in the form y equals k times x. You'll notice that this is a linear function. And it's going to look like this because k is my slope, whether it be positive or negative. It's going to go through the origin because when x is 0, y is 0. The things down here below are ways we could write it out in words. So we would say y varies directly as x, which means, I got to write an equation like this. Or y is directly proportional to x, which means, hey, I got to write an equation like this. And you have to remember that k is never 0. And to name it, K is called our constant of variation or constant of proportionality. Now, this particular type of variation, a direct variation, also extends into our nth power. So notice the n is going to change. We could have quadratics, cubics, quartics, quintics, whatever the question is asking about. And again, a little bit of wording down here saying how you would recognize this type of equation. You could say y varies directly as the square of x, or varies directly as the fourth power of x, that sort of idea. And the same thing with directly proportional. All right, so the next type is the inverse variation. And the inverse variation looks like y equals k over x. This is for some constant k. And again, this is the ways we would read it in order to determine if this is an inverse variation. So we would say y varies inversely as x, or it's inversely proportional. Now you'll notice in any of these statements, even the ones on the previous page, in this statement here, it does never say anything about a k value. It's assumed to be there. It must be there. So you need to use it when you create your equations. So you're going to be creating equations with k's, but you're actually going to be solving for k given some information. You'll see my example here coming up. The last type of variation that we're going to deal with is a joint variation. And a joint variation is just something like this. It's just the product of all of the pieces. So I could say z varies jointly with x and the square of y. Now, this one that I just give up here in the quotes is just jointly as x and y. But here's how you're going to read these equations or these statements. You're going to say z varies. Oh, that means z equals. And then because it's a varying problem, I need a constant of variation. And then I look at what type of variation. It's a joint variation with x and the square of y. So notice how simple that was. Then in order to solve for k, you're going to have to be given a z value, an x value, and a y value so you can solve for k. But again, all that stuff's going to be given to you. All right, so let's look at an example. Let's look at two examples here, actually, and then we'll be kind of finished. So one of our very typical types of problems that we deal with when we deal with variations is one like this, and it deals with volume and pressure and temperature and volume, pressure, temperature. I was thinking something else. All right, so you can go ahead and read through this, but you'll notice this is one of our laws of physics, basically, and here's those keywords. It says varies directly, which means we're obviously going to have a direct variation. All right, so we're looking at volume, which I'm going to name big V. We're looking at temperature, which we're going to name big T. And we're looking at pressure, which we're going to, oh, look at that, big P, just like you thought it was going to be. And we're given some information. And this first piece of information in the problem is usually the information you need in order to solve for K. All right, so we need to write an equation relating pressure, temperature, and volume. So I'm going to move to my next page so I can use that page to write down all of the things that we need to know. All right, so I know, first of all, volume varies. Well, varies means there's my constant. And it says varies directly with what? it says varies directly with temperature and inversely with pressure. Well, now we have an equation. If you look at this, I can count 4 different variables. So in order to solve for one, I need 3. And if you noticed back here, it gave us 3. It gave us a pressure, it gave us a temperature, and it gave us a volume. So I'm going to use those pieces of information to solve for K. So I know my volume is 8,000. I don't know K yet. My temperature is 294 Kelvin. Ooh, what am I using? Don't use the big K for Kelvin here. And my pressure is 0.75. I do a little bit of quick math, and I find out that this is equal to, you're going to hate me here, but it's equal to 1,000 over 49, which means the equation that I can use to solve for any problem now is V equals 1,000 over 49 times temperature over pressure. That's still K times T over P. And you'll notice that's actually answering kind of like our question A. Then our question B is, oops, went the wrong way there. Our question B is, hey, temperature is 300, volume is 7,000, what is pressure? So we can use that. I know my volume is 7,000. I know my temperature is 300, and I don't know my pressure. Again, with a little bit of math trickery, if it's trickery to you, whatever, I can multiply both sides by the reciprocal here, so I can get 7,000 times 49 over 1,000. The thousands cancel, so I'm left with 7 times 49 over 1 equals 300 over P. Cross multiply, solve for P. I get P equals approximately 3. Oh, what am I doing? Wrong numbers. 0.87 kilograms per centimeter squared. See? Super easy. We answered 2 questions. 1, we wrote our equation, and then 2, we used the equation to find one of the values. All right, last piece here for today is, and actually for chapter 3 in general, is simple interest. So notice the key word jointly proportional. So we're going to need to create some things. We're going to say interest is big I. We're going to say principal is big P, and in this case, let's use little t for time because we usually do that in math. And this says interest is, well, that's easy, jointly proportional. Okay, so proportionality means K value. Jointly proportional with T and P. Well, in this particular type of a problem, you're going to be given a T, P, and an I, so you can solve for K, just like we did in the last problem. And then you're going to be using that equation to solve for something else, either time value or principal or interest. You just have to remember that principal represents the amount you put into the bank. All right, so pretty straightforward, I think, for today. Like I said, it was more informational than it was example heavy, so kind of just bear with it. I hope you guys feel good about the quiz today, and I hope you guys have fun with the math. All right, I will see you guys in the morning. Have a good afternoon.